Okay, so now I'm gonna prove really quickly why we're able to do this right here. Basically, when I went and I was like, okay, we have this 2D distribution, um, and then basically you can think of adding noise as every single pixel being sampled from an independent Gaussian distribution. So basically, I'm just gonna prove that this is actually the case. Now, why am I that's like a really good question, right? Like, why am I proving this right now? And the answer is that basically, well, I think this is very useful when you think of like actual images. If you understand how you can add noise. So like if you want to add noise to like an entire image, you can think about it of like as like adding Gaussian noise to every single pixel. And also because like I wondered this myself when I was learning this a while ago. I was just like, how do you actually like add noise, right? That was crazy to me at the moment. So I was like, okay, how do I prove this? Um, so this is what I'm doing right now. Also, one of my friends, he asked for this. So okay, so if we have a multi-dimensional Gaussian, why are we able to do this of like just adding noise to every single pixel itself? Because you can think about like if the distribution was different, you wouldn't be able to do this as taking every single one individually and just sampling from the Gaussian distribution. So we're just gonna prove really quickly why we can do this. So if we look at let's just look at the equation for the Gaussian distribution, and I'll just take it. We will basically look at this equation, but for multiple dimensions. So where are we? Okay. So this is the equation for the Gaussian distribution. So now we just take the multiple dimensions of this. So basically, the equivalent of multiple dimensions is basically like 2 pi dimensions over 2, and then this is like the determinant of this thing, like that, and then this is the exponential function of, well, basically like x minus this. Let me just move everything because it's not gonna fit here. There we go. And then you do this minus 1. Oh, this is transposed actually, my bad. And then you do this thing. Okay, this is basically what you do. Now, this is our covariance matrix. If you know what a covariance matrix is basically just how one dimension affects the other. So for example, if you have like one dimension, 1, 2, 3, basically like it would just give you the variances of how each one affects the other. If we have this and then zeros everywhere else, this would be called a diagonal covariance matrix. And what this is saying is that basically the only dimension that affects the first dimension is just itself, and then the same for the second one, and then the same for the third one, which is basically like, okay, they don't actually affect each other. So these are covariance matrix. So we can start by like just looking at the determinant. So let me just put this into another color so it's not confusing. The determinant of this thing, well, let's just look at what is a determinant itself. So the determinant of A is equal to the, let's just say this is A, B, C, D. This is AD minus BC, right? That's our determinant. So if we look at the determinant of this thing, we can make another example of like a 3D version of this, so like A, B, C, and this would be basically just like taking A and then the other things. So this would be like A, B, C, right? So this would basically be like ABC. So the determinant of this covariance matrix is just, well, all of these things multiplied. So the product with the dimensions where it equals 1. So this is 1, 2, 3 of this thing, I. So okay, we already have this part. Amazing. Then let's see what this thing is. So since we have just variances inside, we can just do the like literally like the literal inverse. So this would be just like 1 over this, 1 over this, and 1 over this thing, and then of course zeros everywhere else. So okay, so we have this one, and then we have this one. So now we can just rewrite this entire expression. Let me just put this in blue. We can rewrite this entire expression as we basically, let's just put it here. Or should I put it? Let's put it here. Okay, so this is transposed, so it's just like x1 minus yeah, this thing, and then x2 minus this thing, and then we put the actual matrix. So what we had before, now I just have two values, so it's easier, and then you just get like the other normal matrix. And then if you remember, like matrix multiplication, it goes like this, right? Like 2 2. I call it like the inverse key. So basically it goes like ta ta. So it go like 2, right? So if you multiply these two together, you will basically get like this thing. And then if you actually like multiply against this, you would just get this squared, right? So you would get this thing right here. Okay, amazing. Now we have what's internal in there, we have what's in there, so we can rewrite the entire thing, and we can just call it so 1 over 2 pi d over 2, then 1 over, we said that the determinant was basically just the product, right? So we can just put the square root inside, and this thing just cancel. So we just say that this is 1 over the thing, and then we have the first part, and then we have the exponential, and then we define the exponential as just the sum of like x1 minus, oh, like not 1, xi minus I over and xi, and then you probably already know that like the sum of exponents is basically just the product. So if you have like ex plus y, this is the same thing as ex ey. So we just take this out, and then we go like let me move it nice. We just take this out. Oops, there we go. And then we just put this here, b equals 1, and then we move all of this over here, and then we just say that like, well, I'm just gonna rewrite it super quickly. The exponent of xi minus I squared over. Okay, so you can see this thing is basically just the product of individual one-dimensional Gaussians. What does this mean? It's basically just saying that like, okay, the probability of each one of these, like the probability of the multidimensional one, so like this multidimensional is the same one as just the product of the unidimensional ones. So what this thing is basically what we call in mathematics like independence, right? So what does this mean? It's basically like, for example, like if you had, I don't know, 2 dice, I mean, you can throw one, and the result of this one is independent, like this one is independent of what happened, right? So you can throw one, and then you can throw the other. So because they are independent, it's basically the same thing here. So basically, you can, if you have a multidimensional Gaussian, or like as we had before, like if you just have these values, you can either sample from like the multidimensional Gaussian, or you can just treat each one of these as independent. And what this basically tells you is that the probability will be the exact same thing. So you can treat this one as independent. So 0.8, and then you can treat this one as independent. So 0.5, and then you can treat this one as independent as well. Okay. Amazing. So this is basically just proving that we can actually do this. Why is this important? Because like once you get into like, we just said that like to add noise, how do you actually add noise to like an image, right? Like a literal actual image. So you would have like a grid, and then you can think about each pixel as doing exactly this, right? It's so cool. So like each pixel is literally just doing exactly this. So I don't know. I feel like that for me that was very useful to learn that like this is exactly and like mathematically proven how you can add noise to each one of these pixels.